Hello again. Thank you very much again for the opportunity to participate in this first national conference on theoretical physics. Now I will be presenting our second work titled Applications on the Generalized Uncertainty Principle on the Statistical Mechanics of Self-Gravitating Fermions, which was conducted in collaboration with Dr. Kamel Urab. Our objective in this presentation is to explore the impact of quantum gravity on quantum mechanics with a focus on how it leads to the generalization of the Heisenberg uncertainty principle. Additionally, we will examine the applications of quantum gravity on the density of states and the mean occupation number in statistical mechanics. This concept will be applied within the Thomas Fermi model, both in the non-relativistic and relativistic regimes, to investigate how quantum gravitational effects influence self-gravitating fermion systems. This presentation will be structured as follows. First, in section 1, we will review the Heisenberg uncertainty principle and introduce the generalized uncertainty principle, which arises in the context of quantum gravity. We will also discuss the density of states at the density of particles. Next, in section 2, we will focus on the Thomas Fermi model. Within the gap framework, we will examine how the model behaves at both absolute and finite temperatures. Finally, in section 3, we will apply the Thomas Fermi model to a fermionic system under gravitational interactions, exploring its implications within the gap frameworks. And we will conclude with some general remarks and perspectives. Quantum gravity and string theory predicts the existence of a minimal length, L sub p, on the order of 10 power minus 35 meters, posing the challenge of observing lengths smaller than this quantum scale. The Heisenberg uncertainty principle, a fundamental principle of quantum mechanics, reveals a curious absence of a minimal length, as we see in the present figure for beta equals to 0, where delta x is plotted as a function of delta p. To reconcile this discrepancy, an essential step is to generalize the uncertainty principle by means of phase space transformation, where xi and pi take the present specific expressions. This transformation leads us to derive a quantum commutation relation paving the way for the formulation of the gap for position x and momentum p. Then, by visually representing the relationship between delta x and delta p, we unravel the presence of the minimal length of the order of the h bar square root beta, where beta is a parameter in the order of the unity. Let's now incorporate the gap into the density of state. In statistical mechanics, the density of state, denoted as A of E dE, is defined as the number of microstates of elementary volume h power d within an elemental 2D dimensional volume of phase space. Now, in order to incorporate the gap modification into the density of state, the microstate elementary volume should be accommodated from h to h gap. Moving now to the density of particles, N of R, which is defined as the number of particles in a given spatial volume. It is obtained by summing the mean number of particles in each energy state, as we see in the following formula, where capital E represents the total energy state equals to the sum of kinetic and potential energies, where the parameter epsilon represents the type of particles epsilon equals to 0 for classical particles, 1 for fermions, and -1 for bosons. Now we take a look on the Thomas Fermi model. The Thomas Fermi model is based on the assumption of an electron gas model, which treats the electrons within an atom as a non-interacting homogeneous electron gas and neglects the explicit electron-electron interactions. In addition, the model incorporates Fermi-Dirac statistics to describe the distribution of electrons between energy levels. Consequently, in the context of the gap framework, the corresponding particle density is given by the present formula. For absolute temperature and in the gap framework, and in the Hab framework, all energy levels are occupied up to the Fermi level, and consequently the density of particles is represented as a d-dimensional sphere in the momentum space with a radius equal to the momentum at the Fermi surface, denoted as Pf. When considering the gap framework, we observe that the density of particles is corrected with respect to the parameter beta, as shown by the following formula and represented in the present figure. However, at finite temperatures, the gas of fermions undergoes thermal excitation, and consequently the density of particles in the gap framework is given by the following formula, where we have replaced the upper bound of integration from Pf to plus infinity. So in such case, we have categorized two kinetic regimes, namely the non-relativistic and the relativistic, as we see in the present formula. The terms including beta in red colors represent the gap corrections to the density of particles. So to return to the Hub framework, we set beta equals to 0. Now, as application, we study the fermionic systems in the presence of gravitational interactions. Consider a system of n self-gravitating fermions, specifically neutrons with mass m, where these particles are bound together by their mutual gravitational attraction in d-dimensional space with spherical symmetry. Then the interaction between a neutron of mass m and the mean gravitational potential phi of r generated by the other masses is given by u of r equals to m phi of r, satisfying the following gravitational version of the Poisson equation. By replacing the particle density n of r with its formula in the gravitational version of the Poisson equation, we obtain the Thomas Fermi equation in the gap framework for the relativistic and non-relativistic regimes. These equations describe the spatial variation of the gravitational potential, taking into account temperature and the quantum gravity corrections. Now, by way of illustration, we have studied the magnitude of the gap corrections in the case of a neutron star for both regimes, relativistic and non-relativistic. Specifically, we have plotted the variation of the ratio of the Laplacian of the gravitational potential under gap compared to HAP as a function of the gravitational potential absolute value of phi of r at fixed temperature for different values of beta. We observe a consistent qualitative effect of gap corrections across different beta values in both regimes. We notice that the threshold at which gap corrections become noticeable differs significantly between the two regimes, where for the non-relativistic case, the corrections appear only for absolute value of phi of r exceeds 10 power 51 SI, whereas in the non-relativistic case, the corrections become noticeable at absolute value of phi of r equals or greater than 10 power 34 SI. This difference arises from the fact that in the relativistic regime, the gap correction term beta p square has a much stronger influence on the elementary volume H gap, and thus more significantly affects the particle density, and consequently this modification in the particle density directly impacts the Laplacian of the gravitational potential through the Newton-Poisson equation. However, when we compare these threshold values with the gravitational potential at the surface of a neutron star, which is about 10 power 17 SI, we see that the gap corrections only become significant at much higher potential in both the relativistic and non-relativistic regimes. This means that at the surface of a neutron star, where the gravitational potential is significantly lower, gap corrections are not perceptible for a neutron. As a conclusion, we have examined the influence of quantum gravity on quantum mechanics, particularly through the lens of the generalized uncertainty principal gap. We also analyzed how quantum gravity affects the statistical mechanics through the density of states and mean occupation number. Applying these concepts within the Thomas Fermi model, we investigated both the non-relativistic and relativistic regimes, uncovering the significant impact of quantum gravitational effect on self-gravitating fermion systems. As a perspective, our modelization of the effect of the gap on the Thomas Fermi model suggests possibilities for experimental setups to detect its subtle influence on the statistical behavior of fermions. While the effect is small, it may become measurable under extreme energy and density conditions, offering a potential avenue for exploring quantum gravitational effects in the quantum realm. And thank you very much for your attention.